Time for a quick side project while I iron out the last few bugs in this Z80 memory card, which are mostly due to this having a lot of breaks in the address bus here. Mostly because of the etching process. So in addition to all of these jumper wires here, I also have to put some bodge wire on the back of it, and I think a couple of these might still be broken, so I have to ohm them all out and all that sort of jazz. And then we'll actually see if this works properly, which would be great. But while I work on that, I also have another project where I'm building an amplifier, and while I own this Rigel DG111 10 megahertz signal generator with its very mirrory display, it is not really suitable for working with vacuum tubes. One of the reasons is that it lacks any decent input protection, which is always great. So if you happen to touch anything over, let's say, 20 volts with the output, you'll immediately fry the thing. And then also, I don't really like the UI, and I just want something simple that will give me a couple of test signals over the audio range. I really don't need a 10 megahertz signal generator. And then, most of all, I want it to be very, very robust, so that I can send a couple hundred volts into the input without destroying it. And being on the budget that I am, I think I will design something that will have this in it. And this is one of the prototypes that I built. This is a Wien bridge oscillator. One type of those, and it generates a sine wave. And I think what I'll do is I'll have this op-amp powered sort of oscillator, and then I'll feed this signal into a vacuum tube just to buffer it, and maybe amplify it up to, 20 volts or so, 40 volts if we can. And then I'll just put a potentiometer on the output so I can dampen it down, attenuate it. And then the thing will basically be invincible, because you'll take the signal via a capacitor from the anode of the tube. So you'd have to do something very, very bad to get through the capacitor, through the tube, to actually damage anything on the tube. So this thing will basically be invincible. So let's look at the options that we have with these oscillators. This is, as I said, this is one prototype I made. And I think it's time I disconnect this and switch off the power supply. And we'll look into the circuits. So this is actually the first circuit that I built for this project. And if you want to know anything about the theory of operation of this, there's a lot of articles out there that describe it far better than I could ever do. And there's also a lot of videos that go into the math behind all of this, which are very interesting, but will not be subject of this video. This will just look into all of the design choices that I made around a given circuit, while not really going into why this makes the circuit work and why you need that sort of feedback here. This will just explore different possibilities of actually building a signal generator from these basic circuits. So what this is your basic circuit with these elements, and then it just has a resistor in the feedback path down here, variable resistor. And it's a split supply because I'm using an LF411 here. I was originally using a 741, but then I substituted the LF411 because it's a little less obsolete, and also it's a JFET input op-amp, which is very nice. Although not entirely necessary here, but I have way more of these than I have LF411s and 741s. And why this might be actually the last opportunity to get rid of my stock of the 741s. I still chose those. So the problem with this is that this feedback potentiometer here is extremely finicky. It's very hard to actually get it set and stable. You really have to have very light touch and be very careful. And I don't know, I don't trust this all that much to actually continue to be stable over the hopefully long time that I'm going to use that. So what we're going to do now is I'm going to put this into my little board holder here, like this, and then I'll have a little look how these are connected, and then we'll hook it up to power and look at the oscilloscope and see what the output from this is. So if you look at the oscilloscope here, you can see that this is working, and it's running at about 1.5 kilohertz, give or take. But you can also see that it is extremely distorted. It's clipping up here and it's clipping down there. This is running off of a 12 volt split supply. So I'm just going to try and adjust that now very carefully with that potentiometer. And there we go, overshot it. And the problem is there is no active element or any element really limiting the feedback. There's just a resistor, and if you don't put it exactly on point, then it's not going to work. But this is a reasonably nice sine wave. There's a little clipping down there, and I can just give it another little nudge here. There we go. This is about as nice as it's going to get. And if I look at the FFT here, I'll just activate that. And we need to set this up a little different now. So I'll go to division, turn that up a little, down, I mean. I want to measure 1 kilohertz. So we'll do 1 kilohertz horizontal divisions, and it just went out. Great. So this is not really stable, as you can see. Just generally a bit of a pain. And now I also need to set the reference level way down, like this, and then we'll also change the scale here, which I should have done first, because now I have to readjust this to 200 kilohertz, and we'll set the reference level again, and then we'll actually put this on screen exclusively, and we can see this is actually reasonably clean. I mean, the sine wave also looks pretty good, but if you look, we get the first sort of harmonic signals down here, somewhere around minus 50 dB volts, which is pretty good. You know, I can't complain about this, and this is it's pretty good peak too. I mean, we can actually stretch this out a bit more. If we go down here, like this, and then bring this up again. See, this is reasonably clean. I mean, there's some harmonic content there, but this is basically down in the noise floor, I think. So this is pretty good, but if we go back, it's very finicky to set up, and I don't really want to do that. And then if I build 5 of those into the signal generator, then I have to set up every single one of them, and then you're in the middle of testing, and I don't know, the temperature is a bit different today, and you have to open your case and get out your screwdriver and reset it again, which I don't really want to do. So let's go to the next circuit. This is the next circuit, and what you can see is that it's almost identical to the last one, except that in the feedback path here, we substituted one resistor here for an incandescent light bulb. And what this does is it gives us a different resistance value for different temperatures. So the filament in a light bulb, the resistance actually increases with temperature. So if it's, I don't know, 20 ohms down here at, I don't know, 1 volt, as you increase the voltage and therefore increase the temperature, the resistance of the light bulb will actually get larger. So it would be, I don't know, 100 ohms here at, I don't know, 5 volts. And what this gives us is control over the current here. This is like a constant current device, because if the voltage is increased, then so will the resistance, and therefore the current will stay about the same. You can see that this has a curve to it. So it's not the best constant current source. There's also implementations that use a JFET for this. They are a little more involved, but these also work fine. I think mostly because light bulbs are not as common anymore, and also they burn out after a while, so you have to replace them. But if you run it at fairly low current, way below the maximum rated current, then your light bulb will probably last longer than your op amp. Also in this, I'm also using an LF 411. And here's the board. Just focus on this. And as you can see, here's a tiny little light bulb. I actually tested all kinds of different light bulbs. But these seem to work very well. These are just small little, I think these are Christmas ornament bulbs or something like that. I have still a ton of them. So way more than we'll ever need for this project. And I think you can still get those on eBay or something. So yeah, also the board on this didn't turn out quite as nicely as on the other one. Where the ground plane is actually solid, while here it looks like, yeah, it's a bit rubbish. But still, it works. I actually remembered to put a proper split supply on here, so I don't have to lift the leg of the op amp. So let's take another measurement here. Same deal as before. We'll just hook it up to our plus and minus 12 volt supply. This is plus 12 volts. This is ground. And this is minus 12 volts. And you can actually see if I remove one of these, the light bulb actually starts glowing. Well, just did. There. Now it glows. So that has actually to do with the feedback path here. I'll just hook this up. And the other thing about this is I also put a potentiometer on here. Although if you find a suitable value for your light bulb with something like this, you could just solder this in temporarily, then tune it up, and then solder in the right resistor that you want. But yeah, this is a little less touchy. This is a 500 ohm pot, although 200 would probably have been better. We'll go over the values once we have our ideal circuit for this application. For now, I just took any old value and just tried the different circuits. So I think it's time we go back to the oscilloscope and look at the waveform here. So as you can see, this generates an even nicer sine wave, albeit this is at a different frequency. This is at 77 Hertz, which is just what it came out at with the components I put in there, which is 10K and 100 nano. So if you look at this sine wave, this is really quite nice. Even if we magnify down into it, this looks really reasonably clean. So let's turn up the scale here and then go into the FFT mode again. And we'll go into exclusive and we'll adjust this a little. So the horizontal divisions are 1 kilohertz, which is quite unsuitable for what we're doing. We should go to 50 hertz is actually quite good, or 100, even better. So as you can see, go up here. This peaks out at about 4. I'd say this is 4 or 5, and then we can see the first other signals at around minus 35 or something like that. And this is also reasonably clean. So I'm quite happy with that. There's, well, I suppose this is at, I see my scale here, this is 100. So if this is 100, yeah, this is 70, and this should be about double that. Yeah. This is at around minus 35. So yeah, I'm pretty happy with that circuit as it is. I had that running for a while, and well, this looks horrible now. Why is it doing that? I'll just tap it slightly. Well, there seems to be some variation in the amplitude now. But this is quite possibly due to the light bulb not being warm enough yet, because this will settle down once the light bulb reaches sort of its equilibrium temperature. But I mean, I could give the potentiometer a little twist here. No, it doesn't seem to change anything. Oh, yeah, that almost fixed it now. So yeah, but I mean, some variations in the amplitude I really don't mind. This is going into like low-tech tube amplifiers, mostly just for my own enjoyment. So I don't mind it much if there's a little variations in the amplitude. And this is, if you actually look at it, this is the it's about 6 volts peak to peak. It's probably around 200 millivolts or so. It shouldn't matter all that much, as long as the frequency is reasonably clean and the amplitude is reasonably constant. I really don't mind it much. And I mean, now that it's warming up and I've fiddled with the controls a bit, it seems to be getting better. So once this is in an actual enclosure, it will probably get better, because one of the reasons why this is fluctuating like this is probably because I'm sitting in front of it and talking and therefore breathing on it and therefore cooling down the lamp housing. As you can see, if I actually touch it with my finger and cool down the lamp, this gets much smaller. So once this is already properly enclosed, it will probably be much less of an issue. So the next thing we need to think about is the power supply for this project. And while at first I wanted to build up a little sort of inverter circuit or split supply using the 7660, originally by Intersil, I think. Now everybody makes them. But the issue with that is that the circuit takes a reasonable amount of current. I mean, each of these oscillators takes about 5 to 10 milliamps, as I have them configured now, which is quite a lot actually. And then also, I'll probably have a vacuum tube buffer in it later, which means I also need high voltage of at least 100 volts or so. So I went to my pile of transformers, and I found this thing here, which is pretty beefy actually. This is a large transformer, but it has 12 volts out here, and then also 20, 0, 20. So I could easily make a plus minus 15 volt supply here and a 12 volt supply here, which then I might even take out to 2 jacks so I can have an op-amp power supply, an additional one. I mean, that's always useful. Maybe even put a switch in there so you can switch off the signal generator and just use it as a power supply, because you can never have enough power supplies. So, and then also 12 for the auxiliary logic, and we can even generate the high voltage for the vacuum tubes by just tripling this. Put a little tripler in there. We have 40 volts. There'll be 80 and 120, which is perfectly fine for the EF80 or other tubes that you can use with fairly low voltage. For the power supply, I'd like to do something like this down here, and we'll go through the circuit now, which starts with the 3 inputs from the transformer, which this is 20, this is 0, and this is 20. And then for the op-amp supply, we just go through a bridge rectifier into some bulk capacitance. Here, split, this is ground, center tap is connected to ground, right? Also, smaller cap on here. because these have different charge and discharge characteristics, and so you get better ripple filtering by having a smaller cap, like 100 nanofarads, and then a large bulk cap. Then going through a 7,815, and this is a 7,915. So this is a negative voltage regulator, it's a positive voltage regulator, giving us regulated 15 volts, plus and minus, reference to ground, reference to the center tap. Again, some output filter capacitance, and then we go out and have 15 volts, plus 0 or ground, and minus 15. So this is just your basic linear supply. This is very much textbook. And then for the vacuum tube, we're going to have a 2-stage full wave rectifier that takes advantage of the center tap. And the nice thing about this is that actually your high voltage here, which is going to come out to about 120 volts, which will be plenty for simple tube buffer, is referenced to ground here. It's not reference to this or this, it's reference to the center point here. And therefore you avoid any issues with having a different ground here than here. And this is just your standard multiplier, really. And if I need more than 120 volts, which I don't think I will, I could easily add another stage. The only thing I'd have to do then is probably make these capacitors a little larger, so I get a little more current. Also, I've got non-polarized caps in here, but on the actual prototype of this I built, I've got polarized 22 microfarad at 36 volts, with this being the negative side on all of these. So going towards there is the negative side on all the capacitors. So let's look at this prototype that I built, which is our large transformer here. And then I've got the bridge rectifier here, which is this bridge rectifier. This is a little adventurous, isn't it? And then I've got the multiplier build up on here. Never mind these smaller caps, I put these in first, but then I realized I probably need larger electrolytics. And let's just build this up like this. And if I turn this on, you can see that I've got 20 volts on one of these legs, minus 20 on the other, and here at the tip of the multiplier I've got 120 volts, which is plenty. And then also we've obviously got 40 volts in between here, 37 point something, but that's fine. So this should all work out. I think next I'll make a board, and then we'll decide on which values to actually put which frequency values to put into this device. So I think I want to limit myself to maximum of 5 bridge circuits, because I mean I could build 100 of them, but what's the use? And then just get overly complicated. I think 5 frequencies is perfectly fine for diagnosis of radios and just to test the odd amplifier. That should be perfectly fine. And I'll just roughly equally space them over the audio range. So I don't know, have one at 50 hertz, have one at a kilohertz, have one at 5 kilohertz, and then have one at 10, one at 20 or something like that. Or maybe 50, 500, 1K, 5K, 20. Well, it's more logarithmic than linear, but yeah, I'll think about that and then we'll see. So now that we have the power supply and the actual circuit figured out, we can look a little bit on the system as a whole. And what I want to do is I want to have 6 separate oscillators, 5 of them being fixed frequency, so I can easily swap between them and always have them tuned up. And I want to have those on switches, and I'll just draw this down as a block diagram here, I think, which is oh, my blocks have to get smaller. I'm running out of paper. So these are the 6 oscillators, and the first 3 of them I want to have like this on a switch, and this goes out to 1 B and C jack. That's over here. So this is oscillator, 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 and oscillator. And this is a switch. I draw a box around this, probably make it more apparent. And then this is a B and C. So with this you have 3 fixed frequencies already, and then I want to have 2 additional fixed ones like this, and then one of them, the last one, I want to have variable. And we'll look in a second on how you would get a variable frequency from that bridge circuit. And this, I primarily want to have this for sweeping and getting frequency response curves and stuff like that. And that I want to have on a second BNC. Oh, and then if you want to switch from the higher to the lower frequency range, you can just change your BNC over. Or if you want to have 2 channels, then you can have 2 channels, which is nice. So for the frequencies, I think I want to have 50 Hertz here. Then the next should be 1 kilohertz, 5 kilohertz, 10 kilohertz, and 20 kilohertz. There's an H missing there. There's a nice diagram. Well, so here we have our schematic again, and if you look at this, here's these high and low pass filter elements that basically determine the frequency. And the frequency is set by the following equation, which is Fr is equal to 1 over 2 pi RC. So if you look at this, if we make this capacitor here variable and also this capacitor variable, and if we gang them together, we could easily get an adjustable oscillator, which is nice. I mean, we'd probably also have to make this adjustable, so we can actually change the feedback path here, because we probably have to tune this up as we go up or down in frequency. So where would you get a dual ganged capacitor? variable capacitor. And this is actually not all that easy, because nowadays the only variable capacitors you find are trimmer caps, and these are really not suitable for an instrument like that. But I have a couple of Ds, which are variable capacitors out of old radios. And the nice thing is, these suit this application rather well, because you have two sections. This one actually has four, but most of them have two. But you can just gang these together by connecting these pins, or you don't. Doesn't matter. You could even make a sort of range switch. If you just switch these over to here, then you have the smaller capacitor and the larger capacitor. But these look internally. You've got this shaft coming through here, and this is connected to this moving section here, to these moving plates. And then you've got these pins down here, which are connected to the static plates. And so what this looks like is you have your first plate here, and then your second plate, which is immediately connected to these two, are connected together to the third plate. And then I messed it up. So you've got your first plate, not connected to the second plate is connected to the third plate, and then you've got your fourth plate, and that goes to another pin. So this is your capacitor internally. And if you look at this, this actually looks a lot like what we have here. You could just connect this upper pin here, this middle pin to the feedback path, to the non-inverting input here. Feedback path is over here, but and then this second one goes over here, and then you'd have yourself a variable oscillator. And I think I'll do that. And maybe I'll use another capacitor, because this actually has 4 plates, and might be useful to have one with 4 plates. And why wouldn't I use one that just has 2 if I only need 2? So I think the next thing I'll do is basically put all my 6 oscillators and switches and the power supply that we designed on a board. So this is the final circuit that I came up with, which is just really 6 of these single elements stacked together with a single power supply. And the power supply is the thing that we looked at before, which is this. I made this board, and it's partially populated already. It's relatively large, but I don't mind. I suppose we could have just used quad and dual op amps to cut down on the chip count, but then again all the passives would have stayed the same, and I don't think it would have given that much reduction in board size. And then also I quite like using single op amps, and therefore you can have a nice modular circuit, and you can put this all in a design block and just plop it down. Since this is a one-off project, I don't really mind the little bit more soldering that I have to do, and the slightly increased routing from having to connect power to all of those. So I'll build this up, and then we'll do some tests, and I think then we'll call it a day. And the next video on this will have the vacuum tube buffer and basically the case, and I don't know, installing the switches and all of that. But we're at this point mostly done with this. So I'll solder this up, and then we'll do some measurement. So here's this board all assembled. I actually decided on using this last one here, not as a variable frequency generator, but as another fixed frequency generator with a fairly low frequency, even lower than this first one here. So why I did this is because, first of all, I couldn't get the variable frequency to work really well with the capacitor I had. And then also, I don't really need it if I want to sweep something, there's way better ways of doing that. And I can still use my other function generator if I really wanted to. So either I'll make a variable frequency generator in another video, or I'll just use this fixed one here, because all I really want to do with this is not high performance measurement, but just use it for simplicity. If I repair an amplifier or something, have a 50 Hz signal or a whatever signal that I'll just easily plug a cable in and then just hook it up to something. Instead of spending 20 minutes on setting up a function generator to do what I want it to do. So I think what we should do now is knock over the tripod. And after we knocked over the tripod, we should hook this up to power. And then have a look at frequencies this puts out on the oscilloscope. So here's a look at the oscilloscope screen. Let me just get my probe here, and I'll just connect this to ground and go to the first channel. And then also switch on the power supply, which always helps. So let's just get this down here a little bit. We can see this is 8 volts peak to peak, fairly nice sine wave. If we spread this out a little, this is fairly nice. 68 Hertz. Go to the next channel. And we can see this is 1.7 kilohertz. This is the only one that is actually a little out. Let me just tune this here. There we go. This one is a little out in frequency. So I might change the capacitors or the resistors, because I want a 1 kilohertz signal there. That would be ideal. 1.8 is really a little high. So we go to the next channel, which is 10 kilohertz, and also this looks really nice. I'm not doing FFT on each and every one of those. We did that before. We can see this. These oscillators are actually pretty good. So let's go to the next one, which is almost exactly 20 kilohertz, which is also nice. And then we have this, which is a little low, and you can influence it a little bit as you tune it up, but not much. But I think I'll just have to live with that. 4.2 kilohertz. It's close enough to 5, really. Doesn't matter all that much anyway. And then we've got this, which is the 15 hertz signal. I'll just have to make my time base a little longer here. And also, you see, this is not the cleanest signal you've ever seen. It's pretty low at 15 hertz. And this is a nightmare to tune up. So feedback is just right, and now I killed it. I think this was actually pretty well set up already. Yeah. It will do. It will do. You can also see that this has a much lower peak-to-peak of around 1 volt. Although ideally I'd like all of those to be down at 1 volt, because this is pretty much line level then. But we'll see about that in the next video, where we'll build the amplifier for this. This is going to have, as I said, this is going to have a vacuum tube amplifier on its end. So, well, the only real reason to do that is because it's a little more resistant to injecting high voltage into the output. But you could just as well do that with a MOSFET, really. I like putting vacuum tubes and stuff. That's what I do. It's fun. So, yeah, I think we'll call it a day. And I'll see you for the amplifying case build in part 2.